Hi, my name is Taylor Plattner, and I will be talking about identifying field sites that have high biosignature preservation potential in planetary-analog brine environments. Mars is proposed to have undergone a shift from a relatively water-rich world with near-neutral pH toward a more arid environment that became dominated by saline and acidic waters induced by extensive weathering of the basaltic bedrock. This is marked in the rock record by a shift from clay-dominated rocks to sulfate-rich minerals and opaline silica. And from the various aqueous mineral images detected, many locations on Mars show evidence of lacustrine environments that indicate diverse aqueous conditions. And as I talk about lacustrine environments throughout this talk, all I mean when I say lacustrine is being associated or related to lakes. And if you can imagine various lacustrine environments across the surface of Mars in the past, during the Noachian era, the problem with understanding these lacustrine environments is that we don't know how truly habitable these environments really were, because much remains to be understood about the early environmental conditions on Mars. In addition, we also don't know how this transition from wet to dry affected the preservation of potential biomarkers, so much remains to be understood about early Mars and its environmental conditions and the preservation of potential biomarkers in these lacustrine environments. We are slowly learning what early Mars was like from various rover missions that explored past water environments on Mars, such as Spirit, Opportunity, Curiosity, and now Perseverance. From the various images that have been returned to us from these rover missions, it's revealed lake beds that are geochemically complex. For example, hematite blueberries that were imaged by Opportunity, and cross-bedding images seen by Curiosity. And from these various images, it indicates that the features that you see on the surface of Mars had to have had long-term interactions with water to produce the features seen here. And on Earth, we know when you have these long-term interactions with water and rock, the composition of your surface water and groundwater is largely controlled by the reactions of water with rock and minerals that it's associated with. And so these water-rock processes can influence the pH, salinity, water activity, and bulk chemistry of your water. And so these water-rock reactions are really important in terms of habitability and how this could affect the preservation of potential biomarkers. And on Mars, we only can look at the rocks that were influenced by lake water. However, with analog lakes on Earth, such as the Western Australia transient lakes, we can actually understand these water rock processes and understand how habitable these environments were and how it could potentially preserve biomarkers over time by looking at these analog lakes that are going through these active wet-dry cycles. And so we can actually understand more about these water rock processes. From these lacustrine environments, we know as they go through a dry stage that they evaporate out various minerals, such as gypsum and halite. And I'm focusing on gypsum and halite in this talk because the analog lakes I'm talking about are either halite or gypsum dominated. And as we know, when these lakes go through a dry stage, they evaporate out these minerals, and when they do this, they can entomb biosignatures. And we know on Earth that various evaporites have been documented to preserve cells or molecules for upwards of thousands to millions of years. And this is just an example on the left of preservation in gypsum, and on the right is preservation in halite. So we can identify these lacustrine environments from orbit by identifying either gypsum or halite remotely. And when we do this, in turn, we can also identify areas that have a high biosignature preservation potential. The analog lakes that I'm interested in are called the Western Australia transient lakes, and they're really unique to Mars in terms of their age and composition. These host rocks that the lakes sit on are about the same age as the Hesperian and Noachian terrains on Mars, and in addition, they have a similar composition to various lacustrine environments on Mars, such as Meridiani Planum and Gale Crater. And in addition, these lakes are also interesting because they host a wide range of geochemical conditions, including pH, salinity, and temperatures, which we think that Mars could have had a wide range of geochemical conditions in the past. And this image is just showing what these Western Australia transient lakes look like. And as you can see, there's multiple of them. And so what I'm going to mostly be focusing on in this talk is using remote sensing to inform site selection of these lakes. So down selecting from hundreds of lakes to a small section of lakes to go sample in situ. As I was saying earlier, the Western Australia transient lakes go through these wet-dry cycles, and as they do this, the geochemical conditions change. And so what I'm showing here is a schematic diagram going through each of the stages, and as they do this, their geochemical response to that stage. And so the first one is the wet stage, or the flooding stage, in which all your evaporites are basically dissolved. And in this stage, you're going to have the most basic water, and it's going to be the least saline. And then when you slowly evaporate out water, you're going to start to form your precipitates such as halite and gypsum, because these Western Australia transient lakes are gypsum or halite dominated lakes. And when you evaporate out these minerals, this is when you can attune biomarkers, and this is when your pH is going to become more acidic and more saline. And then finally, in your dry stage, this is when you've evaporated out all your water and you have these thick halite and gypsum beds. This is when your lake chemistries are going to be the most acidic and the most saline. And so motivation for this is trying to identify these cycles from orbit so that we can influence our sampling time so that we can capture both the wet and the dry cycle, so we can capture how these lakes are changing over time and how that is affecting habitability of the system and in turn affecting preservation of biomarkers. So how do I identify these wet-dry cycles from orbit? I did this by using Landsat 8 data from USGS, and I completed band ratio images, specifically using band 5 and band 6 of Landsat 8 because these bands uniquely define the distribution of gypsum. And specifically, I'm focusing on gypsum right now because these lakes are either halite or gypsum dominated. And what you're seeing in this image is a spectrum of gypsum, and this is showing where band 5 and band 6 of Landsat covers. And so this band 5 is covering a highly reflective portion of the gypsum spectrum, and the band 6 is covering a highly absorptive feature of the gypsum spectrum. And when you take a band ratio of those two bands, what you'll get in the return image is showing that the bright areas are going to indicate gypsum. And so that's what I'm going to show in a couple of slides when I show my band ratio images. And really quick, I just wanted to show where these lakes were at on a map. So all the red dots are the Western Australia transient lakes, which are documented in the literature. And I basically looked at all of these lakes over several years to see if I could identify whether they're going through wet-dry cycles over time. And so what you'll see in the return images is that this southern grouping of lakes acts differently than the rest of these lakes, the eastern, northern, and central lakes. And these are just based off, grouped off by their geographical location. And these southern lake groupings act differently because if you look at the precipitation and climate data, this location gets more average rainfall than the rest of the lakes in local winter in Australia. And so that's what you'll see in the return images. Okay, so what I'm going to show in the next couple images are these two subsets of lakes. So on the left is going to be in blue, it's going to be the southern region of lakes. On the right in red is going to be this small subset of the eastern grouping of lakes. So this is southern region, and then this is the eastern region. And this is just a color image of the lakes. And on the top row is going to be local summer in Western Australia, and the bottom row is local winter in Australia. And what you'll see, again, in the southern region of lakes is that they act differently than the rest of the lakes. And you can really see this in January and July. And this is because in local summer, this is when these southern grouping of lakes are going through a dry stage, and then in July they're going through a wet stage, whereas these eastern grouping of lakes you can't really tell. Okay, so this is the band ratio images that I did to indicate that gypsum was present. Again, this is the southern region of lakes, and this is the eastern grouping of lakes. And this is the band ratio image, not the color image. So this is, again, local summer is the top row and local winter is the bottom row. And so what you'll see that is different in the southern region of lakes rather than in the eastern region is that these southern region lakes are really going through a dry stage and a wet stage. Again, this dry stage is when you've evaporated all your minerals. This is going to be the most acidic and most saline, whereas in the wet stage, you've dissolved all your minerals and it's going to be the least saline and the most basic. So we want to sample both of these times to understand what's happening over time in these Western Australia transient lakes. And whereas in the eastern groupings of lakes, you really can't tell what is happening over time, whether it's going through a wet-dry cycle or not. Based off the remote sensing results, most of the lakes don't show seasonal variations. Only the southern regions of lakes really show a trend as they go through these wet-dry cycles. And this is important when we actually go sample measure these lakes in situ, so we actually get context when we sample. And from these results, it's really motivation for a second sampling season for the southern region of the lakes. So we want to go to the Western Australia lakes and sample twice at different times in the local winter and local summer so that we capture these wet-dry cycles that the southern region of lakes are going to. Whereas the other group of lakes, such as central, eastern, and northern lakes, we can really sample at any time. Now to complete this work, I went to ground truth with a spectrometer to identify gypsum in situ so that we can verify whether what we're seeing in the remote sensing images is actually gypsum. In addition, I want to further map and identify gypsum using the spectral angle mapper classification in ENVI. And then lastly, I want to extend present work to include halite by using ASTER data because you need the thermal infrared to identify chlorides. And I'm going to do this by using a method developed by Alice Baldridge, which was then applied to identify chlorides on Mars. Thank you.